Alright, so we're going to look at the chain rule here. I've just wiped my tears away. I just did a 25-minute video for you guys on chain rule. And yeah, I didn't capture any audio. So, you know, the good news is this is take 2, so it should be better than take 1, I guess. So the glass is half full. Chain rule, we're going to use it when we want to find derivatives and when we want to find the derivative of composition of functions. So in order to first understand how to be able to apply the chain rule, we first have to make sure that we're clear on composition. So you know, composition is when you're evaluating a function at another function, which might make no sense to you, but for example, let's say you had like one function was x squared. So whatever your input is, just square it to get the output. Let's say another function was the sine function. We could compose these functions. We could take sine x and plug it in for x squared. You know, and turn this thing into sine of x squared. What that is, right? That is f of g of x. You know, another way you could compose it would be to plug f into g. So you could take x squared and plug it in for the x in sine x. So that would be sine of not x anymore, but sine of x squared. So you have two different compositions here, right? And two different opportunities to apply the chain rule. You know, just the formula itself, the derivative of f of g of x is the derivative of the outer evaluated at the inner multiplied by the derivative of the inner. So I use like a lot of, you know, I use the words outer and inner and derivative. You know, the biggest thing there, though, I think is outer and inner. You have to understand which is which. For the first example here, that red bullet, the inner is sine x. The outer is x squared. So think, if you plugged sine x into x squared, you'd end up right here. Okay. If you did it the other way around, like let's say you thought you had identified the inner and the outer, but let's say you accidentally flip-flopped them, right? What if you said the inner was x squared and the outer was sine x? So that says plug x squared into sine x. If you did that, x squared into sine x, sine of not x, but sine of x squared. Oh, that didn't match what I had over here, right? So you have incorrectly identified the inner and the outer. And probably when you first start with this, I would pick an inner, pick an outer, and then compose them. Actually plug the inner one into the outer and make sure that you get back to what you started with. Because if we can't consistently do that, then we're not going to be able to obviously get the right answer. So, you know, once you get your inner and your outer identified, then you're just going to apply the formula. Okay, so do some stuff up here. The derivative of the inner is cosine x. The derivative of the outer is 2x. Okay. So I'm going to do the derivative of the outer 2x. But it's the derivative of the outer evaluated at the inner. So right there for x, you need to plug in the inner function. Okay, that's sine x. So this is like the derivative of the outer evaluated at the inner looks like this. Then you're going to multiply by the derivative of the inner, which is just cosine x. So and that's your final answer. That there is the derivative. That is the derivative of sine of x squared. or quantity sine x squared or sine squared of x. Okay. The other one, you've got this blue bullet. Okay, you flip-flopped your inner and your outer. The inner, that's the x squared, and x squared gets plugged into the sine function. So you do the derivative of the outer, cosine x, evaluated at the inner. So the derivative of the outer evaluated at the inner, multiplied, that's the last step, multiplied by the derivative of the inner, which is 2x. Let's do another one. So recognizing composition is key. Right? You know you need to use the chain rule when you're asked to find the derivative of a composition. So let's say, I don't know, e to the natural log of x. This will be a fun one. So I got two functions. The inner is natural log of x. The outer is e to the x. You know, you could even start by saying, it seems like I have two functions. The natural log of x and e to the x. And then write them and then think, which one is the inner? Am I plugging the natural log of x into e to the x, or am I plugging e to the x into natural log of x? Well, if you notice, this is e to a power, e to the power of the natural log of x. So you're plugging natural log of x in here. Right? So the natural log of x, that's your inner, e to the x is your outer. This one's going to work out nice. Some of you may already be saying, why are you doing this problem? Okay, so we can just, let's list their derivatives real quick. That's 1 over x. That's a cool one. That's e to the x. The only function whose derivative is itself. Alright, so the derivative of the outer evaluated at the inner. Derivative of the outer evaluated at the inner, multiply by the derivative of the inner. Oh man, look at this. I already made a mistake. I was gonna, I put 1 over x here. I'm like, I shouldn't have 1 over x twice. I'm looking right here. I did the derivative of the outer evaluated at the derivative of the inner. Okay, that blue circle, that should just be the inner. So that was your natural log of x. Derivative of the outer evaluated at the inner. That's right there. Derivative of outer at inner. And then this last piece here, that's just your deriv of inner. Okay, so you're like, hey, that doesn't seem like a big deal. E to the natural log of x times 1 over x. Okay, that's fine. This can certainly be simplified. I'm going to come back and simplify it in just a sec. I'm going to find the derivative of the natural log of e to the x. Natural log of e to the x. And then we'll come back and simplify. So I've got my inner, so a new problem, and I got an outer. Okay, the inner is e to the x, whose derivative is just e to the x. The outer is the natural log of x, whose derivative is just 1 over x. Okay, so the derivative of the outer evaluated at the inner. Derivative of the outer evaluated at the inner times the derivative of the inner. Wait a second. That's just 1. That's weird. I didn't think that would be 1. So, like, okay, let's look at why that's 1. Let's look at what I started with. Okay? So we still got to come back up to this thing, this smiley face. So, why was that 1? Well, think about this. Like, think about natural log of 10. Okay? That right there, that is the exponent you put on e to make 10. So, like, watch this. E to the natural log of 10. So e raised to the exponent you put on e to make 10. So take e, and you're going to put an exponent on it. That exponent you put on it is the same exponent you put on e if you want to make 10. So e raised to the exponent you put on e to make 10 is just 10. Or natural log of smiley face. That is the exponent you put on e to make smiley face. So come back up. E to the natural log of x. I'm going to grab this thing right here. Okay. E to the natural log of x. So I'm looking at this yellow thing, right? First off, natural log of x. What's that? In green. Okay, that is, in green is, that's the exponent you put on e to make x. So in green is the exponent you put on e to make x. So if you put that exponent on e, you should make what? Well, that's just x. E raised to the exponent you put on e to make x is just x. So, see if I can keep track. So this purple thing right there, that's just x. So you've got x multiplied by 1 over x. And that's just 1. That's just 1. So that the answer from, the first one we did, that's simplified as well, right? That was just 1. So both of those are 1. So come back to what you started with, what you were asked to initially find the derivative of, e to the natural log of x. You were asked, I said, d dx, e to the natural log of x. And what if you said, you know what, Mr. Lund, before I find the derivative of that weird thing, what if I simplified what was in parentheses? What would that simplify to? Okay. I say, all right, so what is that? And you'd say, that is the exponent you put on e to make x. So, you know what? Why don't you just go ahead and put that exponent on e? That's what's happening here. Put that exponent on e. What are you going to get? X. So that's the same thing as finding the derivative of just x. Well, what's the derivative of x with respect to x? 1 times x. What's the derivative of 1 times x with respect to x? That's just, that's 1. Cool. So there's something neat with natural log and of x and e to the x. So the whole point of that was I started you with a composition. Okay. Let's find the work. It's down here. I started you with a composition. It was a little tricky, right? The inner was natural log of x. The outer was e to the x. And it turns out, what if I can simplify what I'm given before I actually, worry about finding the derivative? Can I do that? Yes. So here you started with something that actually simplified to x. And if it were me, I'd much rather find the derivative of x with respect to x. That's 1 than what I was given there. So let's do a couple more. Okay, we'll do a quick one. So maybe you want to like practice this one. This will be let's go some mess to the -5th. Cosine x minus 9x to the 4th. Okay, inner, outer. Inner is cosine x minus 9x to the 4th. Its derivative, well, this minus sign right here is really convenient, because like you can do the derivative of each of those terms separately. Oops. So the derivative of cosine x is negative sine x. The derivative of 9x to the 4th is 36. So you got your minus in yellow. Minus 36 x cubed. So the derivative of this blue is here. And the derivative of this green is here. So we have the derivative of the inner. A little ahead of myself. Now let's do the outer function, which is x to the -5. It's the derivative of that. Okay, march the -5 out front, so -5x to the -6. Okay, so derivative of the outer. Evaluated, so at the inner. So where you see x in purple right here, that's where I'm plugging in the inner function. And that was cosine x minus 9x to the 4th. So we got the derivative of the outer evaluated at the inner multiplied by the derivative of the inner. Negative sine x minus 36x cubed. And we're done. Yeah, I mean, you might be able to simplify that a little, but you're fine. Stop there. That's good. Okay, one more. Then I'm going to go take a nap. All right, we'll make it difficult. Let's go the derivative of e raised to the sine x to the pi power. What? That's okay. Don't worry. Inner. Sine of x to the pi. Outer. E to the x. Yeah. If you plug sine of x, quantity sine x raised to the pi, if you plug that into e to the x, you'll be looking at what we started with, okay, right here. So sure, you've said, I have identified an inner, and I have identified an outer. They are appropriate. And that's pretty sweet. I actually know the derivative of the outer. It's just e to the x. Now, if I just got my hands on the derivative of the inner, I'd be set. I'd nearly be done with the problem. So no biggie. You're like, you know what? I just want to find the derivative of the inner function. Derivative of sine of x to the pi power. I'm like, well, that's a function in a function. No biggie, right? You got an inner, and you got an outer. Okay, the outer is x to the pi. The inner is sine x. The derivative of the inner is cosine x. The derivative of the outer. Okay, it looks nasty, but it's not, okay? It's just x raised to a number. So it's the same thing. You're going to march that out front and take one away. So pi times x to the pi minus 1. So I go, okay, derivative of the outer, pi x to the pi minus 1, evaluated at the inner. That's just sine x, multiplied by the derivative of the inner. All right, so just take that result, right? All that work went into simply finding the derivative of the inner function from back here. Like, you kind of have to compartmentalize it. Like, say, okay, well, I'm gonna act like I'm working on a new problem right now. It's kind of like a puzzle. You're like, okay, if I could just solve this problem, then I'd be done. You're like, well, to solve this problem, I need to solve these other two problems. So you start working on those other two, and they might expand and build new problems. And eventually, you get to the end of that tree. And you're like, okay, well, I solved this problem for a reason. What was I trying to answer? And you keep stepping it backwards and backwards and backwards. And that's kind of what we've done here. So we're not done, but we said, I remember that I had an inner function, and I had an outer. And I was tasked with finding each of their derivatives, because I was using the chain rule. So now you just got to write down the pieces. The derivative of the outer, evaluated at the inner. So there you go. The derivative of the outer evaluated at the inner times, and this is where a bunch of legwork went in, the derivative of the inner, pi times sine x to the pi minus 1 times cosine x. And we did it. We got it. That right there. That's the derivative, right, of this. So that was chain rule twice, only because you had a composition of 3 functions. Good job. I know that was a lot. I appreciate you sticking it out and getting through it. And hopefully you found the video helpful. And yeah, good job.